Hello class, welcome to another lecture. So today we will be discussing about the proportioning of retaining wall. So see, what you have to understand is a retaining wall consists of many elements, right? So first, of course, the height to which it has to retain the soil, that is dictated by site conditions. Other than that, you have to determine the thickness of the stem. You have to determine the thickness of the base slab towards the top. So this is the top portion, this is the heel portion. You have to know the thickness of top portion, thickness of heel portion, overall length. So there are many things that needs to be considered for a retaining wall proportioning. uh, Also there are stability checks also which come into picture. So unlike a beam, if you take a beam for instance, what we'll do is we'll quickly assume some width, and only then depth remains to be proportion. So unlike that, there are many factors for a retaining wall. So in today's lecture we will be discussing about only one aspect. uh, it is about the position of stem on base slab. So remember, we told that this is the stem. So the stem will have a vertical face and a slightly inclined face which is on the soil side. uh, I'm sure you might have studied this in geotechnical engineering, and which will be resting on the base slab. So today's lecture will be discussing how to determine the position. This how to determine the position of the stem on the base slab. So only that aspect we will be discussing today. Now whatever I am going to discuss today, it will be common for both gravity retaining walls and counterfort retaining walls. So remember, there are three types of walls in your syllabus: gravity, counterfort, uh, sorry, not gravity, sorry, cantilever retaining wall, counterfort retaining wall, and basement wall. So whatever I am going to discuss today, they are applicable for both cantilever retaining wall and counterfort retaining wall. Now it can be proved that the economical design. So the thing is, we are going to arrive at a criteria from economical considerations. Of course, economy is the base of all design. So from economical considerations, it can be proved that the economical design can be arrived at if the resultant of soil pressure. So remember, R, we already seen it in the earlier class. It is the resultant of soil pressure exerted on the retaining wall. So it can be proved that the economical design is achieved when R, the position of R is aligned with the vertical stem. So if R matches with the vertical face of the retaining wall, then we can achieve economical design. So how can you prove that? Well, we will discuss that in today's lecture. So for the derivation, let us look into various factors. First of all, R is the total reaction, right? So R is dependent upon what all things. So first of all, it is dependent upon the weight of the sulfate of the retaining wall plus the soil that is retained on the heel portion, and to a certain amount this portion as well. So R is the total vertical reaction, which is a resultant of all the weights or sulfate of retaining wall plus the vertical force of the due to the sulfate of the soil. So it depends on the total weight, and which also indirectly depends on this length. So here I have drawn a full retaining wall. So this is the vertical stem. So whatever soil is resting on the heel portion, that is also contributing to the weight, right? So this R, which is a function of the total weight, is also a function of this length. Okay, so this length is nothing but it includes the length of the slab up to the heel portion. Now let us look at this figure. So for that derivation, there are certain things we'll consider. First of all, it's an approximate derivation. So the weight of retaining wall towards the top portion, which is actually also contributing to W. or the total weight of the retaining wall plus soil, we will neglect. So in this particular derivation we will neglect that. Now let us take x. So as we said, this r depends on the total weight, which depends on the length of this portion, because depending upon how much length you have, that much weight of soil will be uh, acting downwards and contribute to r. So let us take the total length x as a proportion of L. So obviously L is higher because L also includes the length of the top portion. So let us take X, which is the portion from the vertical stem to this heel portion, as alpha X into L, where alpha X is obviously some coefficient which is less than 1. Now assuming a average unit weight for retaining wall and soil. So remember, here it is retaining wall, which is concrete RCC, which might have unit weight of 24 or 25 kilonewton per meter cube, sorry. And you have soil, which will definitely have a lesser unit weight. Maybe on an average you can consider it is 18 kilonewton per meter cube. But disregarding the fact that both are having different self weights, if you consider some weighted average or equivalent unit weight, considering the proportion of areas, and if that equivalent unit weight is assumed as gamma E, okay, then you can say that the total weight of this entire rectangular portion, it is nothing but gamma E, which is the equivalent self weight, into h is the total height, into x. Okay, please pardon me the inclination of the vertical stem. So this portion of the vertical, this side of the vertical stem will be truly vertical. So in what I drawn, it is not. So please excuse me for that. So the total weight is gamma E into h into x, unit weight to this area. Of course, the length of the retaining wall is always unity. So that will be equal to W. So R equal to W equal to this. Now alpha x, we have already assumed it as alpha x into L. So this expression will be gamma E h alpha x into L. Now the reaction depends on the x value that we already established, because that much as x increases, the self weight will increase and R will increase. And we can also say that, see, the L is the total length from toe to heel. Okay, so just like we have taken x as a proportion of L, right? So like that we can also take the length from heel to the reaction point as LR, okay, which is as also a proportion of total L. So LR, you can take it as alpha R into L, where L is the total length of base slab. So here it was alpha x into L. The location of the resultant is alpha R into L. Now once you get alpha R into L, now one of the things here you have to note is, see, this is like the bottom of the footing, right? This entire length of base slab is like the bottom of the footing. So the proportion of alpha R will dictate the pressure distribution of soil underneath the base slab. So if this alpha R is half, it means the reaction is acting at the center of the base slab, which means you will have a uniform pressure distribution. Okay, otherwise, if suppose alpha R is something like 2/3, so if alpha R is 2/3, this it will shift more towards this side. So it means the pressure distribution under the base slab won't be uniform. It will be triangular, like just like you might have studied in the case of eccentric footing design or things like that, or even in the theory of raft design, which I discussed. When the reaction is eccentric, the pressure distribution won't be uniform. Anyway, that's just for understanding. That's not the main point here. So let's so here what you have to know is the alpha R can be fixed by us depending upon the pressure distribution we desire. So if you put it 0.5, if you want a uniform pressure distribution, of course it will be a little uneconomical, but you have to choose a alpha R of 0.5. Otherwise, for triangular distribution, it is 2 by 3. So that is alpha R, which is a constant, which you can, not a constant, you can select it based on the type of soil pressure distribution you require at the bottom. Okay, so now let's come to the main part. So how can you prove that R is or the design is economical when you have R at the position of vertical stem? So for that, let us use equations of equilibrium. Now the entire setup is in equilibrium. So you can take moment about this point, moment about the point where the reaction is acting, base reaction is acting. So basically you will have only two forces. Even the frictional force will, since it is acting along the same point, it won't contribute to moment. You have a moment due to the total load W, and you have a moment due to the active pressure PA. So this moment is PA into H by 3, and that due to W is this total length LR, which is nothing but alpha R into L minus this distance. So this distance you can take it approximately as half of alpha x L by 2, or sorry, half of alpha x L. Now it's not exactly same because we discussed the concept of equivalent unit weight. So actually unit weight is more towards the retaining wall side, but approximately you can take this as half of the total length. Okay, so the lever arm that's going to cause the moment due to W is LR minus half of alpha x L. So that's what we have done this here. So you are equating those moments. So when you rearrange and you take alpha L by H on one side, then you will get that is equal to square root of CA by 3 to alpha R alpha x minus alpha x square. Now we know that height is a constant. Height of the retaining means height of the level of soil up to which you need to retain the soil, it's constant, you cannot change that. And so of course height here also includes the portion below the ground on the toe side, but overall it's a constant, it doesn't vary. But what you have to control is the length. So you can say that for economic design L by H should be minimum. So for L by H to be minimum, the denominator should be maximum. So the denominator is 2 alpha R alpha x minus alpha x square. So for that to be maximum, we can say that it is maximum when alpha R equal to alpha x. Okay, which means in this diagram, if alpha R equal to alpha x means the reaction is exactly at the position of the vertical stem, vertical straight edge of the vertical stem, which is what we had initially stated. So that is the proof for that. So this is the condition. Of course it is approximately because some approximations we are used. So based on this condition alpha R equal to alpha x, you can substitute it back into this expression and we'll get the expression for L by H minimum 1 by alpha R CA root of CA by 3, and for a given height we'll get the expression for L minimum by giving sending H to the other side, and then using the same expression for alpha minimum you can get the expression for alpha x min. So this is, so remember this was our x. So for L minimum, when you substitute that you will get x minimum, minimum width required towards the heel portion. So that's about that. Now here in the derivation we had used a level backfill. Now if you have a surcharge or a sloping backfill, we already discussed that in the case of surcharge it is like you are adding additional height. So only thing that will change is instead of H that we are using here, in the case of H, a surcharge you will have H plus HS, that to account for the effect of surcharge as well, or in the case of sloping backfill it will be H dash. Okay, so using that this expression, we can get the length of x. So once you get length of x, you can decide the length of toe portion, assuming a suitable pressure distribution, soil pressure distribution, because we said that the proportion of alpha r with respect to alpha will determine the shape of soil pressure distribution under the base slab. So when we are doing trial and error, first we will assume that it is we will go for a triangular distribution, which means we will choose this particular assumption, alpha r is as 2 by 3. So when alpha r is 2 by 3, we will get that length is 3 by 2 x. Of course, we will do, that's the initial assumption. So if it does not satisfy soil pressure requirements, we will revise it. Okay, so this much is for today's lecture. So remember, today what we discussed was just one aspect, which is equally applicable for both cantilever retaining wall as well as counterfloat retaining wall, which is the position of the stem, vertical stem with respect to base slab. So it should be positioned such that the soil reaction comes close to the vertical side of the stem. Okay, thank you.